So we have got the concept of the emission spectra. Now the next one is absorption spectra. Absorption spectra means what? Electron will jump from the ground state to the higher energy orbit. Means emission spectra, what I said, that when electrons transit from higher energy orbit to lower energy orbit, then they emit certain radiation. That's why the spectral lines, they are known as the emission spectra. But when an electron jumps from lower energy orbit to higher energy orbit, then it absorbs the radiation. That's why it produces dark line in that particular dark line of that particular frequency. That's why these spectra are known as the absorption spectra. So what is the basic thing you have to remember regarding the absorption spectra? During the formation of absorption spectra, electrons or atoms, it jumps from the lower energy orbit, lower energy level to the higher energy level, first point, and second point, it absorbs radiation, it absorbs excuse me, it absorbs radiation, it absorbs energy. Alright, that's why it is termed as absorption spectra. So if you consider the absorption spectra for Lyman, Balmer, Paschen, bracket, P-fund, then you just see what I have done. The arrows I have just inverted. Arrows are from Lyman series, means in case of Lyman emission spectra, all was their destination was first orbit. Now, for Lyman series of absorption spectra, their starting point will be the ground state. You see the arrows are opposite. They are jumping, electrons are jumping from ground state to second, third, fourth to infinity. Then they will give you the Lyman series. Like that, when the electrons will jump from the second level to some other higher energy level, they will give you the Balmer absorption series. Like that, for Paschen, they will jump from third to higher orbit. Is that clear? And so on. But one very important point you have to understand, an interesting point regarding the absorption spectra is that if you consider the atoms at ordinary temperatures, they generally remain in the ground state. Alright, at ordinary temperature, as all the atoms, they remain in the ground state. So, at ordinary temperature, only Lyman series can be obtained. Is that clear? But if you want to take the atom to the higher second state, then also it needs the temperature almost equal to sun. You know, inside sun, hydrogen are there. Is that clear? So if you consider the hydrogen series produced by the hydrogen present in sun, due to their high temperature, the atom may stay in the second level. But it is very difficult to take them to the third level. That's why in case of solar spectra, means if you consider the hydrogen spectral lines formed by the hydrogen present in sun, then Lyman and Balmer series are available. But after that, it is also very difficult to get the series. Is that clear? So, although in case of emission spectra, one may have all the 5 series, means the Lyman, Balmer, Paschen, bracket, Fund series. But in case of absorption spectra, only the Lyman and Balmer series for hydrogen available. That too, at ordinary temperature, only Lyman series available, and at the temperature nearly equal to sun, means in solar spectra, the Lyman and Balmer absorption series are available. So these are all the concepts of the emission and absorption spectra. Once again, I am reminding that these two topics are very important for your board exam, especially the diagrams. So please do learn and practice it. So you see, when we are considering the Bohr's theory, then Bohr's theory is also not unable to give us the complete description of the structure of an atom. That's why Bohr's theory has also certain limitations. Bohr's theory also having certain limitations, and these limitations you have to understand, and once again this is a very important topic for your board exam, so you have to learn it. So one by one I am discussing the limitations of Bohr's theory. First is that in case in Bohr's theory, the first point is that it can explain only the formation of line spectra by hydrogen-like atom. Already I told you, hydrogen-like atom means what? The atoms which are having only one electron like hydrogen. But the atoms which are having more than one electron means multi-electron atom, the spectra formed by multi-electron atom cannot be explained by using Bohr's theory. Second point is that if you consider any spectral line, although it is appearing as one line, but by a high resolving power microscope, if you look at the line, then you will see that the line, it has for closely spaced several thin lines. Okay, here there is no, okay, I am just sorry. Suppose there is a single line you are observing by an ordinary microscope. Now, if you use a fine microscope, then you will see that there are several closely spaced lines like this. Is that clear? These are known as the fine structure. So, fine structure of spectral line. Why fine structure of spectral line is formed? That Bohr's theory cannot explain. Okay, this is the second point. The next point is Bohr's theory cannot say anything about the relative intensities of the spectral line. What will be the intensity of the spectral line? That Bohr's theory cannot say anything. Then fourth point is that if you take any spectral line, then if the spectral line is under the effect of the magnetic field, means if the atom is placed in a magnetic field and the spectra is produced, then you will see that spectral lines get splitted into different lines under the effect of magnetic field. That is known as the Lyman effect. Like that, if an atom is subjected to an electric field and the spectra is formed, then you will see that spectral lines, it gets splitted into different lines under the effect of the electric field. That is known as the Stark effect. Now, what is the cause of the Lyman effect, Stark effect? Bohr's theory cannot explain. Is that clear? Then next one is Bohr's theory cannot explain the wave nature of electron, and Bohr's theory do not give us any idea regarding the distribution of electron in different orbits. In different orbits, how many electrons will be there? We cannot get any information from Bohr's theory. So whatever I have discussed, I have written it on the whiteboard. So point wise and in short, so you to note it down and also learn it for your board exam. So what is the first limitation of Bohr's theory? It fails to explain the spectra of multi-electron atoms. It can explain only the spectra of one electron atom. What is the second limitation? Bohr's theory cannot explain the fine structure of spectral lines even in hydrogen atom. Then third point, it does not tell anything about the relative intensities of the spectral line of an atom. Fourth point, the theory fails to explain Lyman effect and Stark effect. What is Lyman effect? That I have written within the bracket. Means splitting of spectral lines under the effect of magnetic field. And what is Stark effect? Splitting of spectral lines under the effect of electric field. So if you want, you can drop this. Means you can just write that the theory failed to explain Lyman effect and Stark effect. Then fifth point, it does not explain the distribution of electrons in different orbits. And the last one, it gives no information about the wave nature of electrons. All these 6 points you are supposed to learn and prepare for your board exam. These are the limitations of Bohr's theory. Now, what are the uses of Rydberg's constant? Rydberg constant is used to determine the ionization energy. Already I have discussed this topic, that ionization energy is E infinity minus E1. Okay, if you consider hydrogen atom is having only one electron. Okay, so if you can take that electron from the ground state to infinity, then it means that you are taking out the electron from the atom and the atom is getting ionized. So what is the ionization energy? It will be E infinity minus E1. What is the energy of the E infinity level? 0. And what is the energy of the first level? You know, it is minus RHC by n square. So you see, it will become minus RHC by n square. So plus RHC, and n is equal to 1 for 1. first level or the ground state. So if you substitute the value of R, Rydberg constant, then the value comes 13.6. This is for hydrogen atom. Is that clear? So this is the way one can, using the Rydberg constant, you can find out the ionization energy. Then the second use is that this is the most common use, and you have to solve the numericals also. Just understand it. It is used to determine wavelength of any line in any spectral series. You know, for any spectral series, it is given by 1 by lambda is equal to R into 1 by N1 square minus N2 square. So suppose you are considering, as for example I am saying, suppose you are considering the Lyman series, and the first line. So first line means it will be the transition between 2 and 1. Is that clear? So it will, N1 will be 1, N2 will be 2. So when N1 1, N2 equal to 2, then just by putting the value of R, you can find out what is the value of lambda. Okay, so this is the way one can find out what is the wavelength of any spectral line of any series by using the concept of Rydberg constant. What is the Rydberg constant value? I hope you can remember. 1.090 into 10 to the power 7 per meter, and 1 by lambda is known as the wave number. So that's all about this chapter. Thank you, girls.